Hello again. This is Math 2134 coming to you from the College of DuPage, and the title of this lecture is Higher Order Derivatives. As always, please be an active learner as you watch this video with pencil and paper in hand and using the pause and rewind buttons as needed. The topic is higher order derivatives. The derivative f prime of a function is also a function as itself. As such, the differentiability of f prime may be considered, and we would proceed to calculate that by looking at the limit of the difference quotient, where this was f prime of x plus h minus f prime of x all over h exists or doesn't exist as h goes to 0. In other words, it is the derivative of the first derivative. The function f double prime obtained in this manner is called the second derivative of f, just as the derivative f prime of f is often called the first derivative of f. Continuing in this fashion, we are led to be considering higher order derivatives, third, fourth, and so on and so forth. These are the notations. For a while we use primes, and when it gets more complicated counting the primes, you put an exponent there that it looks like an exponent, but is really parentheses in, and that stands for the nth derivative. Or sometimes this notation is used at COD. This is mostly used in my differential equations class. If we're writing y equal f of x, we put the primes on the y, or we use this notation, which is Leibniz notation, which I will use quite a bit because it's really probably the best notation, or we could do this. So examples are worth a lot more than words. So let's find the derivatives of all orders of this polynomial. So it's y equals f of x equal all of this business. So when we take the first derivative, and you should check and make sure that you are practicing all these, but this is what I get when I take the first derivative. When I take the second derivative, I'm taking the derivative of this and get this. The third derivative is the derivative of this function. That's what you get when you simplify it. The fourth derivative is the derivative of this. I get this. And the fifth derivative is this. And if I take a sixth derivative, or anything higher than 5, I'm going to get 0. And the derivative of 0 is just going to be 0. So you see this actually does have derivatives of all orders. Here I'm asking you to find the third derivative of this function is y equals f of x is equal to x to the 2/3. What is its domain? Now, there is a point in this that the domain of the derivative can be different than the domain of the function. The domain of this function is all real numbers. This is the picture of what it looks like. But when we take the derivative, and in fact you might realize this just graphically, there's an abrupt change of direction that happens here at 0. So we're going to find that the derivative doesn't exist at 0. Okay, so anyway, so this is just the power rule. So y prime is going to be 2/3 x to the, I subtract 1 from the exponent, is x to the minus 1/3. Then when I take the second derivative, it is 2/3, and that's going to be minus 1/3. That is a minus 1/3, and then I subtract 1. This is x to the 4/3. And when I simplify that, I get this. Again, this is a negative here, negative 2/9. And so if I take the derivative yet again, I do this and this. Now this becomes positive. I subtract 1 yet again, and I get this, and I can put that in the denominator to simplify. So you see the common domain of the functions f prime, f double prime, f triple prime is everything except 0. And there's the graph. An important note, always simplify an expression before differentiating it to obtain the next order derivative, because it could get to be quite a mess. Not so much in this problem, but in many other problems it will be a mess. So doing the algebra is useful in between differentiations. In fact, I think we'll see that on this one. We want to find the second derivative of this function, but this is going to involve the chain rule because it's got this business raised to the 3/2. So the first derivative is going to be 3/2. This business raised to the subtract 1, that is 1/2, times the derivative of what's inside, which is 4x. Now, if you took the derivative of this, it would be, it really could be quite a mess because you got multiple constants around and things like that. But if you simplify, it's a little tamer. But when we take the derivative of this yet again, it is going to be the product rule because you have one function times another. The first function is going to be simple, but the second one involves the chain rule itself. So now we're going to take the derivative, so it's going to be the first function times the derivative of the second plus the derivative of the first function times the second. So you see this is going to be, when I take the derivative of this, it's going to be 1/2. This business, now subtract 1 to the minus 1/2 times the derivative of what's inside, which is 4x. Here it is just the derivative of 6x is just 6. But now you got quite a bit of simplification to do. And so we end up with this. When we factor out the common factor, we get this. And if we put the radical back in, and we get this. Can you imagine what would happen if we were taking the third derivative? Algebra is indeed your friend. Just as the derivative of a function f at a point x measures the rate of change of the function f at that point, the second derivative of f, the derivative of f prime, measures the rate of change of the derivative f prime of the function f. And the third derivative of the function f, f triple prime, measures the rate of change of f double prime, and so on. Again, the derivative is measuring instantaneous rates of change. This is an important physical example because the rate of change of position with respect to time is velocity. The rate of change of velocity with respect to time is acceleration. So here we're telling that s is equal to 4t squared. This is the magnetic elevated train we've talked about many times. But now we want to talk about acceleration. Well, velocity is going to be given by the first time derivative, so that's going to be 8t. But then we take the second derivative to get the acceleration. That's the derivative of the velocity, and we will get 8. Now the units on this would be, the acceleration would be 8 feet per second per second. And that's normally abbreviated 8 feet per second squared in your science classes. We can apply this to more than just magnetic trains. So here we have a ball thrown straight up in the air from a roof of the building. The height of the ball is measured from the ground is given by s is equal to minus 16t squared plus 24t plus 120. S is measured in feet and t is in seconds. Find the velocity and acceleration of the ball 3 seconds after it's thrown in the air. Now this ball is going to go up and go down, so this is actually a very useful physics problem. So the velocity is going to be found by taking the derivative with respect to t of this function. So you're going to get minus 32t plus 24. And the acceleration is going to be the second derivative of this function and the first derivative of this function. So we'll get minus 32. That is the acceleration due to gravity. So when we plug in 3, we'll get that the velocity I'm plugging into this equation is minus 72. That means I am going down. The acceleration is 32 feet per second, and that also is downward because it is minus 32. Another interpretation of the second derivative, we talk about applications in this class a lot, this time from the field of economics, is suppose you have the consumer price index between years A and B. So this is talking about how much does it cost to live. The first derivative and we call that I. So the first derivative of I at a point gives the rate of change of I, and that is going to be this. And that is called the inflation rate at time t. The second derivative gives the rate of change of the inflation at t. Now it is possible for I prime to be positive and I double prime to be negative. In fact, we see that here. I prime, it's always increasing, but when you look at the slopes of the tangent line, they start decreasing. This tells us that at time t, the economy is still experiencing inflation. The CPI is increasing, but the rate at which the CPI is growing is in fact decreasing. The rate it is growing is decreasing. This is precisely the situation described by an economist or a politician when he or she claims that the inflation is slowing. One may or may not jump, in fact you cannot jump to this conclusion, that the quote, that the price of goods are about to drop. They're just raising, the increase is slower. This example deals with that. So here is the economy function where this represents the CPI of an economy, and that corresponds, t equals 0 corresponds to the beginning of 2002. You want to find the inflation rate at t equals 6, and then we're asked to show that the inflation was moderating at that time. Well, inflation is going to be I prime over I. So you find the derivative of this function, and you get minus 0.6t squared plus 6t, and then we evaluate it at 6, and we get this number. But since we have a denominator here, we're going to plug 6 back into this function. Again, keeping track where you're plugging things is an important skill. So when I do this calculation, the rate of inflation is this amount, or approximately 8.7%. So now we're going to look at I double prime. So that's taking the derivative of the first derivative. So I get this, and I plug in the value of 6. I see that this is negative. That means that I prime is decreasing, and conclude that the inflation was moderating at that time. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.